Okay, so this is video 3 in exercise 7 of chapter 4 of the Advanced GIS book. And in this video, we're going to take these geologic or soil band ratios and run a principal component analysis looking at the variation in all of these soil ratios to see if we can kind of really highlight all of the geologic variation with just kind of maybe 3 different principal components, allowing us to display a map of geologic difference in red, green, and blue, which will be quite a lot of fidelity and detail that we'll be able to see, hopefully. Um, and so we're going to use a tool called Principal Component Analysis. Okay, so that is in, I believe, yeah, in multivariate statistics, principal components. Boom, there it is. And so all we actually do is feed in the various raster bands, and it looks at, for each pixel, how these different bands of band ratios relate to each other. You know, uh, does iron oxides go with clays? Maybe not, right? But some of them are going to go together in terms of brightness and others are not. It's going to look at all the statistical relationships between each of the bands. Just think of it like 7 dimensions. And it's going to look for a kind of common axis of like the most common trend and create a principal component trend through that. That'll be a principal component number 1. And that'll capture like a lot of the variance in the data. And so it's kind of like taking all of these 7 kind of axes of 7 dimensions and trying to convert it into the top 3. Um, kind of dimensionally collapsing things from 7 to 3 or 4, showing almost all of the same things in less total dimensions. Uh, that's one way to think about it. Definitely read through the chapter on this and other resources as well to get kind of wrap your head around this principal component thing. Um, but to do this and do this well, uh, we have to be careful because it'll allow us to feed in any bands in here. So I could be careless and put in band 2. If we go down to band 2, we'll notice that the values go up to 31,000, whereas all these band ratios are not more than a couple of dozen in terms of total magnitude. And so if we feed in something that's kind of off scale, it'll really outweigh everything else and it will dominate the result. And so when you do principal component analysis, you want things to be kind of scaled similarly, kind of using like units. In this case, they're unitless because there is a ratio. But you know, I am a little worried if I look at Gausson's goes all the way to 22, whereas most of the other ratios are just a couple. Um, and so I would expect that Gausson's is going to be playing a big role in what we see in the end in this principal component analysis. Uh, that's okay, potentially, since it's so tied to what we're looking at. But, you know, if you really wanted to get kind of overly anal retentive about this, you could kind of normalize each of these ratios into their range and say they're from 0 to 1, transform each of them to 0 to 1 relative to their range if you didn't want one to outweigh the others at all. I'm not going to do that. We're just going to feed each of only the ratios in. So don't mix units. We're not doing that. Don't put these in twice. So I've got oxides, silicates, Gaussons. Oh, let's be careful about how we order these. Um, let's do it in the order that we ran them. So it was clay, iron oxide. Let's go in. The reverse of what they're listed is how I entered them and how our tables have been organized. And that will just be easier for me to think about and remember. And so, yeah, before I hit go, I'm going to make sure that I've got 7 different things there. And, looking at these ratios helps with that. Okay, and then this is key. So we're going to output our multiband raster. I'm going to call it BRD PCA, principal component analysis. And there's 7 principal components. There's always 7 that come out, but we're going to see that only the first few are really important. But always output your data file too. So we're going to call this BRD PCA data. Because this is going to, the data file is basically a text file or basically a table that you can look at and kind of understand what happened in this multivariate statistical analysis. It'll show you how each of these different band ratios relate to each other, what correlates with what and what does not. And it'll show you in the end how the principal components matter. So principal component 1 is going to matter the most, 2, 3, 4. As we get to 5 and 6, we're going to see they basically don't capture hardly any variance. They're not going to have much of a weight. So that's what we're trying to do, is collapse things down to less total components, focus in on those top few principal components. And then also it'll show us how those top few principal components relate back to the input variables, all these band ratios. And so BRD underscore PCA underscore data. Okay, let's run it. So we're going to want to look at that data file. And in your labs, you're going to want to analyze it in pretty good detail. And so I'll look at that with all, in this video tutorial, we'll look at it together and try to think about what it means a bit. I don't know how long this takes to run. Hopefully not too long. In the meantime, while it's running, I could clean things up a bit. Get rid of some of these things. Zoom out a bit. Full image. It's processing pretty quick. In a whole Landsat scene, there are quite a few pixels, but the reality is 30 megapixels. It's not that much. If you have a fairly good computer and processor, it shouldn't take too long to run. And generally, you're not going to do this over multiple Landsat scenes because you don't, the reflectance and whatnot as you go across bigger areas of land, different time periods, probably not a great idea to mix that for this analysis. Okay, so, we have some colors, interesting. And yeah, can see some areas look yellow, some purple, etc. Hope this was a good area to do this. Not sure. We get into the mountains here, we start to see what look like bands of geologic formations. Some things look different, some don't. Interesting. Okay, so let's go into symbology here. And so what is it doing? So it's, why is it colored like this? So red is colored with whatever is band 1, band 2. You can see actually there's 7 different bands, okay? I'm going to go not to percent clip, but standard deviation here and see if that changes anything. Ah, there we go. Okay, so yeah, so that's pretty key. So yeah, there is my PCA with a standard deviation stretch. And in the mountains, it shows a lot of various colors, which is encouraging because as we look, there's kind of ridges and things. It's probably different rocks. In the playa here, we can see different colors. These are different salt concentrations. Out here in the alluvial fans, you can see that the active channels look different than the inactive fan surfaces, and maybe even they look different as you get further downstream as minerals get sorted out by density. Things look quite different in the cities even. Some of these volcanic areas look quite different from one another, suggesting that maybe the different weathering is different from different ages of the volcanism, or maybe the different mineralogy is different. This mountain ended up looking quite similar in the end, maybe because it's covered in more vegetation than we expected. Okay, so that is our principal component image. What does it all mean? Okay, and we can change how this looks. If we change what's band 2 and band 1, it's going to look different here in a second. Right, so, and we could, change in band 4 for band 3, and it's going to look different again, right? But probably best to go with the default until we at least look at the data table. Okay, so where is that data table? And I hope it's gonna show it to me. Yeah, there it is. So BRD text. Okay, so these tables, they look like there's nothing there. And you can open them in a text file, but this works. Okay, so yes, so what is shown here? So it shows you what input rasters were added. So clay, iron oxide, etc. A little bit weird that it says band 1 after all of them. Don't pay attention to that. And then the first thing that it gives you is a covariance matrix, okay? And so layer 1 versus layer 1, etc. This one is a little bit weird to think about. So come down to this correlation matrix. So these are the input layers on both axes of this table, or this matrix, sorry. So clay versus clay. Clay is clay, so they are 1-to-1. That's what that's telling you. The next one is clay versus, I think it was iron oxide. And what that shows you is, like, if we were to do like a linear regression between those two things in the pixels, that would be kind of like the slope of the relationship between this. So slightly positively correlated with one another. The next one, which is clay versus ferrous iron oxides, is negatively correlated just a little bit. And then clay versus ferric iron is more negatively correlated. Wow, number 6, so the number 5 is the Gaussons. That's slightly positively correlated. Maybe more than slightly, it's 0.2. But look at this. Number 6 is super negatively correlated. So where there's a lot of clay, there is definitely not a lot of ferrous silicates. And remember, clay we found in like the lake beds. There's not a lot of iron silicates in the lake bed, is what it's telling us. Okay. Iron silicates maybe are heavy, they don't get that far out, right? Um, and then another negative correlation is ferric oxides, similarly. So we can see that what clay isn't and is related to across the landscape amongst all the pixels. And so in this correlation matrix, you're always going to see like a 1 in the center, right? Going through because you're at some point comparing that thing to itself, and they're exactly the same. And so that should be the case, okay? Um, I think it's interesting to look at what correlates strongly together. So like in number 2, in these iron silicates correlates very strongly with number 4, which was ferric iron, and somewhat with ferric oxides. Okay, cool. That makes some sense. Number 3, ferrous iron oxides is negatively correlated with a lot of things. The only thing it's positively correlated with is number 6, which is ferrous silicates. So the two ferrous things are correlated together, makes sense. The Gaussons, not too much with clays, but Gaussons are correlated with iron oxides. Gaussons themselves tend to have a lot of oxides, so that makes sense. Also, ferric oxides. So oxides correlated with oxides. Ferrous silicates most strongly with the ferric oxides. Oh, did I read that wrong? Well, you get the idea. Kind of want to go through and see what is and isn't related. It's informative. You might do that later as you've thought about it more. But then let's skip down. So what is this showing us? So where it says PC layer 1, 2, 3, 4, 5, 6, 7. So these are principal component layer 1 to PC3, PC4, etc. And then on this axis, this matrix, those are the input layers. So clay, iron oxides, etc. And we'll come down here. It says percent and accumulative eigenvalues. So principal component layer 1 has this eigenvalue, which is the highest here, of 0.06, okay? But let's not pay too much attention to trying to understand what is an eigenvalue right now. But this thing where it says here, this is percent of the total eigenvalues, is 72.3%. So what that's saying is that principal component layer 1 is capturing 72.3% of the variation across this Landsat scene according to these band ratios. So they're able to, by doing this analysis, we're able to see 72% of the variance just by looking at principal component layer 1. Okay, interesting. So what is, oh, I deleted my table of contents. Add that back. Oh. So what does that mean? So we'll have to pull that back up here in a second. But like if we go to symbology for this principal component analysis, BRD PCA, if we go to stretch instead of color, what we see is that band 1 if we go to standard deviation, we can see a lot of the detail in geologic difference with just that first principal component, right? So that's what we've done here. Principal component 1 stretched across the image. We can see darker and lighter areas are showing us geologic difference. These are floodplains, lake bed, different geomorphic surfaces, different volcanic rocks, all show us different brightnesses. And so it's capturing a lot just in that band 1. If I go to band 2, it should be less, but different. So now some things look washed out, but other things do get highlighted differently. And interestingly, it looks like a lot of vegetation. It's quite low value here. Okay, but you can look through at what each principal component band is keying in on or not. In this one, the ag is showing up as super bright and the wet areas. That was band 3. Band 4 is shown here. That looks pretty geologically interesting. Think about that, band 4. Let's go to band 5 and see what that looks like. That's interesting. 6. Also still interesting. And then band 7. Definitely interesting looking. But let's see what those things mean now. Okay, so let's go back to look at that table. Try to pull it up as a text file so we don't have to lose what we've got open here. Okay, so interesting, right? The way this has shaken out is that PC1's almost over 72% of the variance. PC2, 11%. PC3, almost 9%. PC4, 3 to 4%. And then almost 3% in PC5. But only 0.5% with PC6 and 7. So we've at least kind of eliminated the need to use 6 and 7. They're showing us something, but they're not showing us something that's not already shown in the other things. In this case, it shows us that most of the variance is caught up in the first 2 or 3, but then there's some detail in those other ones, so it's not perfectly collapsed everything. And so in our kind of displaying of the 3 colors, you have some choices to make. It probably makes sense to use 1, 2, and 3, but there is some value in 4 and 5 still. Okay. So another thing that we can look at above that, principal component layer, number 1. What is it showing us? Principal component 1, how it relates in terms of the eigenvectors to the input layers. This is similar to the correlation matrix. If it's high, close to 1, it's strongly related, or could be strongly negatively related. So if we look at principal component 1, it shows up pretty big with 5 and 7. 5 and 7, that was Gaussons and ferric oxides. Okay, so by showing principal component 1, we're seeing areas of oxides being quite bright, and areas that were dark will be the negative correlated things, which is 3 primarily, which is interestingly ferrous iron oxides and also ferrous silicates. So yeah, ferric versus ferrous is showing up quite strongly there. If we go to principal component number 2, we see a negative relationship with clays that's pretty strong. and a negative relationship with number 5, which is Gausson's, which is quite strong. And we see positive relationship quite strong with iron oxides and ferric oxides. Interesting. So not Gausson's, but other oxides. And then as we go to principal component 3, we see quite positive with clay, positive with iron oxides again, but then negative with these two. And so I think, if we think about using one color for band 1, 2, and 3, a different color, by using band 3, we definitely showing something with the clays, which has got to be important, right? And so that's different than the other two. We are showing, we got to use band 1 clearly because it's got so much of the variance. Band 2, principal component band 2, is definitely highlighting something slightly different than band 3. But there could be some question of whether or not you might rather use band 4 as opposed to band 2. So what if we mapped 1, 3, and 4 as opposed to 1, 2, and 3? And the reason I might say that is I see a positive high value here for input layer 1. And I also see it there for input layer 2. But I haven't, for input layer 3, I don't really see anything super high until we get to band 4. And so I wonder what that looks like. So let's go, let's compare these. So let's go back to RGB. And we start off with 1, 2, 3. And remember, not percent clip. We got to go to standard deviation. And we're going to stop this video here, and I'm going to pick up with it in a bit in part 4.